So we will start our first lecture. So in these lectures we will first begin with some basic concepts in linear algebra, and then we will go ahead and see some applications, and applications not in the strict sense of the word applications perhaps, but how it helps us understand other parts of mathematics, like say differential equations, things like that. Well, that is, so for example, how linear algebra helps us in say differential equations, things like that. So it's more about the interconnectivity of mathematics that we will be dealing with than about the physical applications. But what happens is these, if once you, so for example, you all know that say differential equations are very applicable in physics. So the application is in a is slightly in an indirect way, and partly this is because we are mathematicians, so we don't really work in physical problems, but we sort of we know so we know that this particular concept comes from this particular physical problem, and we study that simplified model. So that is how we generally work with. So yeah, so that is the basic idea. I don't know how much you know, so that is why, so I will just assume certain things and then perhaps go ahead. So if you feel I'm going too fast or too slow, you can tell me. That's not an issue. I can adjust accordingly. So yeah, and again, some of you might have seen linear algebra before. That's okay. Let us at least revise it, and we will be dealing it with a slightly different approach. In less, like we won't use determinants so much and things like that. So the textbook or the reference for the linear algebra part of this course would be this book by Sheldon Axler called Linear Algebra Done Right. So that's a very beautiful book. I guess all of you should have a look at that book. It's an amazing book. Okay. So when it comes to linear algebra, first we want to understand what a vector space is. So that is the central idea in linear algebra. So a vector space, loosely speaking, is a set where you can actually, or a collection of objects, set which is same as collection of objects, where you can add and you can also scale. Okay. So there is an addition operation between the elements, and there is something else. There is a collection of objects with which you can scale. These things will be called scalars. Scalar meaning that which we use to scale. Like creator is that which creates, right? Something like that. The scalar is that which scales. So something like that. So these scalars generally come from a field. If you don't know what a field is, it's fine. A field, I can loosely say a field is a set where you have addition, you have multiplication, and this addition and multiplications behave well with each other. A good example is set of real numbers or set of complex numbers. These are all examples of field. Set of rational numbers is also a field. So rational numbers, real numbers, complex numbers, these are all fields. Okay. You can assume without we won't lose anything. You can assume that we will be always dealing with R or C. Okay. So it's either the real, whenever there is any field that is in picture, that is either real numbers or complex numbers. So these are the setup which I want to first fix. So now let us try to delve more into this concept of a vector space. So the most standard example or the simplest example, I need a duster. Yeah. The simplest example of vector space would be what is R2. What is R2? It is the set of all x, y, where this x and y will belong to real numbers, set of real numbers. Now on this we can define an addition. We can define an addition on this set, which is defined as follows. So if you have x1, y1 and x2, y2, we can add it as component wise addition. Right? It's x1 plus x2, y1 plus y2. Okay? And we can also scale. How do we scale? If we have a real number c, we can scale it as c into x, y is equal to cx, cy. So basically everything we are doing coordinate wise. Correct? So that is the idea. Now this satisfies certain simple properties. Let us see what are those properties. First of all, it is commutative. That means x1 y1 plus x2 y2 is equal to x1 plus x2 comma y1 plus y2, which is the same as x2 plus x1 comma y2 plus y1, because commutativity of real numbers. Real numbers commute, so you can do this, which is same as x2 comma y2 plus x1 comma y1. So this is commutative. This the vector addition. So okay. So the space where we can add will be called vector space. Add and scale will be called a vector space, and the elements of later that in fact all vector spaces can be seen as an Rn. What this seen as means will be explained by Pranav, and he will in fact show that it can be. Okay. So there is some notion of saying two vector spaces are same. Just like there are we always need a method to say when are two things same, right? So there is some notion like that, and under that notion of equality, every vector space can be sort of seen as an Rn. So in some sense, this is the most general example of something called finite dimensional vector space. We will come what that finite dimensional is. We all know what vector space is. What finite dimensional is, we will come within some time. So, second example. Second example is polynomials. Okay? You can add two polynomials, right? So suppose, say for example, there is one polynomial which is of the form a0 plus a1x1, a1x plus a2x square plus x. Oh, am I writing too small? Okay. a0 plus a1x plus etc. up to anx power n, actually, and b0 plus b1x plus etc. up to bn x bmx power m plus. Okay, we can add these, like we will get a0 plus b0 plus a1 plus b1 into x plus etc. Okay, whether m or n is bigger, depending on that, one will get over first, and then just the other terms will be there and stuff like that. You know how to add, how to add two polynomials. You can also scalar multiply. You can also do scalar multiplication. Just like each of them, you just have to add a c. So you can add two polynomials. You can also scale a polynomial, and it's easy to check that it will satisfy all these properties. And in fact, you can see that actually this is it is in some sense it's easy to see what I was telling earlier. Okay, so in some sense this can be seen as an element in Rn. Correct? This polynomial can be looked at like this. And actually what we are doing is component wise. Each coordinates we are adding. That's what we are doing. Scaling also we are doing coordinate wise. Right? So now itself we are having a glimpse of why, even though this looks like a very different example of vector spaces, actually it's not so different from it. Okay? So this is one example, polynomials. Third is polynomials of degree less than or equal to n. Again, it's easy to see that this is a vector space. Why? Because if you add two polynomials, the degree is not going to increase more than the degree of the highest degree polynomial. So if f is a polynomial and g is a polynomial, if the degree of f is m and the degree of g is n, the sum will have degree less than or equal to m and m, like maximum of m and n, right? Because we are doing this component wise addition. So because of that, if you add two elements, it's not the degree is not going to increase. If both polynomials have degree less than or equal to n, the sum will also have degree less than or equal to n. Similarly, by scalar multiplication also degree is not going to increase, right? So this is also a vector space. So this, in some sense, this contains this, in some sense. So polynomials of degree less than or equal to n is actually contained inside polynomials. Now, a more general example is you can look at continuous functions on, say, R. Okay, continuous functions on R can be added. It can be scaled. Again, it's easy to check that so it's from R to R. Okay, real valued functions, continuous real valued functions on real numbers. Because of commutativity of real number, because of all these, since all these properties hold for real numbers, the same will hold for these functions. Because what you are doing is you are just adding f of x plus g of x at each point. That's what you are doing. Okay, so f plus g at x is equal to f of x plus g of x. This is how, and cf of x is equal C times f of x. That is the addition and scalar multiplication. Similarly, we can actually take a we can take a subset of this which also will form a vector space. The example is you can take C infinity of R. Means you can these are functions which can be differentiated as many times as you want. Okay, so these are also examples of a vector space. Now, in some sense, what we can do is this is the most general. This is contained inside this. This is contained inside this, and this is contained inside this, and this is contained inside this. Right? You can see it because if something is infinitely differentiable, it's certainly continuous. So this is contained inside this. Every polynomial is infinitely many differentiable. So polynomials are contained inside this, and this is contained inside this. We already saw that. So we have actually a containment also. Okay. So this is another example. Third example is you look at a linear equation of the form say ax a1 x1 plus a2 x2 plus etc. up to an xn is equal to 0. Okay. You look at a linear equation and you look at this. You look at a linear equation like this and look at its roots. So roots of something like this. Roots of something like this, okay, is contained inside Rn, and it actually forms a vector space, vector subspace. Is it easy to see, or is it difficult to see? Okay. I think it's difficult to see. Then let us try to show that. Since nobody is, I will സാധാരണ മൗനം സമ്മതം എന്നാ പറയാ. ടീച്ചിങ്ങിന് നേരെ തിരിച്ചാ മൗനം അസമ്മതം. അത് മനസ്സിലായില്ല എന്നാ അതിന്റെ അർത്ഥം. അപ്പൊ മനസ്സിലായിച്ചാ പറയണം. Okay, so we want to see that suppose so we want to see the root of such a polynomial this forms a vector space. So let us look at assume that x1 comma x2 comma etc. up to xn is a root of this linear equation. Similarly, let us say that y1 comma y2 comma etc. up to yn is also a root. I want to show that the sum of these two actually is a root. That's what I want to show. What is the sum of these two? The sum of these two is nothing but x1 plus y1 comma x2 plus y2 comma etc. up to xn plus yn. Okay. Now I want to see if this is a root. What do? I just apply this. a1 into x1 plus y1 plus a2 into x2 plus y2 plus etc. up to an into xn plus yn. I just like this multiplication distributes. Okay, so I can write it as a1 x1 plus a1 y1 plus a2 x2 plus a2 y2 plus etc. up to an xn plus an yn. Now I collect the terms. I write it as a1 x1 plus etc. up to an xn, okay, plus a1 y1 plus etc. up to an yn. Now this is 0 because x1 to xn was the root of this linear equation. Similarly, this is also 0. So the sum of these two, so 0 plus 0 is 0. So this whole thing is 0. Hence proof. So roots of a linear equation actually forms a vector space. Right? Scalar, okay, actually you have to check scalar multiplication also, but I'm sure now you can do that. Okay, it's even simpler than this case. So roots of one linear equation actually forms a vector space. Now another example is, this was one root of one linear equation. Instead you can take a collection of linear equations, finitely many collection of, so you look at roots of A11x1 plus A12x2 plus etc. up to A1nxn, AM1x1 plus AM2x2 plus etc. up to AMN xn. So these are M equations, M linear equations in n unknowns. Okay, the roots of this system of linear equations also form a vector space. Actually, you will again, I will make one more remark. You will see that these kind of, so this in some sense is a linear function. So you will be seeing that actually looking at roots or zero set of linear functions is one way to construct a lot of vector spaces. It's a general recipe to create subspaces. So whenever we whenever we study something in a concept in mathematics, what you should do is you should have enough examples of that concept. So the only way to understand that concept is to look at thousands and thousands of examples of that concept. So we need to be able to create, like, given known examples, you should be able to construct other examples of the vector space, right? So that is one very important thing. So these are all recipes. So yeah, I will just deal with one final example because that will be again useful. It is called MNR. This is called matrices. So a matrix is something which is a collection of objects of the form, say, A11, A12, etc. up to A1n, and I am taking a square matrix. Okay. So you get to AN1, AN2, etc. up to ANN. Okay. And I can add it with another thing of the form, say, B11, B12, etc. up to B1n, Bn1, Bn2, etc. up to Bnn. Okay, I fill all these. So I add this as again coordinate wise addition. Okay, A11 plus B11, A12 plus B12, etc. up to A1n plus B1n. Similarly for all these. So it's coordinate addition. Coordinate addition again gives addition for matrices. You also get a linear scaling also. So in some sense again this is like an Rn itself. Okay. It's just that we are writing it in a square shape than in a long line shape. Something like that actually. Technically speaking it's too different from an Rn. But why we are bothered about this is because we will be able to construct a lot of other examples of vector spaces using this. Okay, that is why we need this. So I will, after the next concept I am introducing, you will understand why I took this example. So the next concept is what are called subspaces. Okay, so we have vector space. Now we have vector subspaces. What is a subspace? So if we have a vector space V, okay, and if we have a subset W in V, we say that this is a subspace if and only if W1 plus W2 belongs to W whenever Wi belongs to W, okay, and CW1 belongs to W whenever W1 belongs to, actually you don't need W, we don't need the I, whenever W belongs to W. Okay, so these are the two kinds. This is what is called a subspace, right? Now, I won't prove it, but it's easy to check that instead of checking both these criteria, we can actually, it is easy to see that something is a subspace if and only if it satisfies an equivalent another condition. The condition is you just take it as C1 C times Wi C times W1 plus W2 belongs to W whenever Wi belongs to W. It's actually just enough to check this. We are actually combining both this into one shot. So it's enough to check this. So this will be useful in our later lectures. That's why we are like, so in this lecture it won't make a difference, but it will be useful later. So it is the same as just checking this. C times W1 plus W2 belongs to W whenever W1 and W2 belongs to W. And C belongs to the field that we are taking. Okay, so this is called a subspace. We need examples of subspaces. Here we have. So this is a subspace of Rn. Roots of a linear equation is a subspace of Rn. Why? Because we saw that it's a vector space. So if you take two elements and if you add them, you still remain in that. If you scale them, they still remain in that. So this is a subspace of Rn. This is a subspace of Rn. This is a subspace of this. This is a subspace of this. The fact that something is a vector space and it's contained inside something automatically means that it's a subspace. So we already have seen a lot of examples actually. So this is a subspace of this. This is a subspace of this, and hence this is a subset of this. Subspace of this. This is a subspace of this. Okay. So we have so many examples of subspaces. Now we want to see other subspaces. Other subspace, that is why we will come to Mn of R. Okay, so I'm sure you would have seen like lot of examples, like say suppose determinant 1 matrices. You take matrices of determinant 1, they form a subspace. Why? Right, because determinant of AB is nothing but determinant of determinant B. So if both the determinant of A and determinant B are 1, then the determinant of AB is 1. So because of that, determinant 1 matrices form a subspace. Right? Similarly, invertible, like this actually here we already similarly like invertible matrices form a subspace. They are called GLNR. This is MNR. So invertible matrices. If A is invertible and B is invertible, then AB is invertible. Why again? Because of the same calculation of like determinant and all that. A matrix is invertible when determinant is non-zero. If determinant A and determinant B are non-zero, then determinant AB is non-zero. Right? If you are not familiar with these ideas of determinants or matrices, don't worry, we will anyway see it again. Matrix will be revisited very in a lot of detail later in class. Okay? So if you are not comfortable with any concept of the matrices, just leave it. It's not okay. As long as you have understood these examples, that's well and good. That's why I wrote this separately, and that was slightly like, maybe you don't know. Because anyway, these are ideas which you will see later. So that time you will remember these things. That is why I was dealing with this.
Maybe we shouldn't call them subspaces, examples, because I and minus I, if you add it to the subgroups.
Yeah. Oh, sorry.
They are not good examples.
Oh, correct. Oh, sorry. I made a mistake. Yeah. Yeah, correct. Sorry. So yeah, correct. Sorry, I made a mistake. Yeah, sorry. I'm really sorry. So what happens is actually addition of two. I actually multiplied them, which is unfair. You have to add them. So that is not a good example. So okay, they are not subspaces. So determinants of matrices with determinant 1 is not a subspace. It's actually just a subgroup. Okay, I made a mistake. Yeah. Anyway, so that's fine. So but anyway, we will actually be seeing a lot of subspaces of MNR also. Okay. What will be one good example? And the sum of two matrices to be in the same thing. Yeah, that is actually difficult. Triangular matrix. Diagonal matrices is a good example. Okay, or triangular matrices is a good example. Symmetric matrices is a good example. Okay, so diagonal matrices, upper triangular matrices, lower triangular matrices. So yeah, there are examples which form subspaces. Okay, so yeah, I'm really sorry for mistake. So yeah, okay, so fine. So these are what are called subspaces of a vector space. I hope till now everything is clear. So now I will rub these. Now what we will see is we will see span of a vector. So if you have a V in the vector space V, we say the set of all elements of the form CV, such that C belongs to the field, which is equal to R or C. Okay. This is contained inside capital V, and this actually is a subspace. Okay, this is subspace of V. If you take collection of all CVs, so if suppose there are two elements C1V plus C2V, they add up to C1 plus C2V. Similarly, if you scalar multiply also, you will still end up. So this actually is a subspace. So this is called a span of a vector. Similarly, if you can take two vectors and take the span, or n vectors and take the span. How do you do that? Suppose we have the vectors V1 etc. up to Vn. Okay, I consider the set of all vectors of the form C1V1 plus C2V2 plus etc. up to CnVn, where each Ci belong to R. I will fix my attention to R. Okay, so this is called span of vectors. Span of vectors V1 to Vn. Okay, this again is a subspace. You can easily check that if you take two vectors of this form, let's say Ci-Vi, summation Ci-Vi and summation Di-Vi, you add them, you will get summation Ci plus Di-Vi. Right? So again, and scalar multiplication also same way. So span of vectors also form a subspace. Span of n vectors also form a subspace. Okay? So these are two important notions. Now what we want is linear dependence or linear independence. Okay? We say that V1 to Vn are linearly independent. From here I will just write Li. Okay. Every time I won't write linearly independent. We say that V1 to Vn are linearly independent if and only if A1 plus V1, A1 V1 plus etc. up to An Vn equal to 0. Okay. If and only if Ai equal to 0 for all I. Okay. This implies that Ai equal to 0 for all I. So this is the definition of linearly independent. A set of n vectors are called linearly independent if they satisfy the condition that A1 V1 plus A2 V2 plus etc. up to An Vn is 0 if and only if Ai is 0 for all I. Why such a definition? Suppose this is true. Okay. So why are they called? Okay. Actually, this is why such a definition is easier if we actually go to linear dependence. There it's easier to understand why a set of vectors which satisfy that condition is called linearly dependent. So what is the opposite of this? The opposite of this is linear dependence. Linear dependence. What is linear dependent? There exists Ai such that not all Ai are 0. Okay. With not all Ai 0, such that A1 V1 plus A2 V2 plus etc. up to An Vn is equal to 0. Okay. So this is the negative of this. There exists a collection of non-zero AIs, not a 0, such that Ai Vi, summation Ai Vi is equal to 0. Without loss of generality, let us assume that Aj is not 0. Right? The jth element is not 0. So then what I can do is I can take all the elements to the other side. I get Aj Vj is equal to minus of A1 V1 plus etc. up to minus of Aj minus 1 Vj minus 1 plus Aj plus 1 Aj plus 1 Vj plus 1 plus etc. up to An Vn. Okay, and we can just divide by this aj. Okay, we can divide by this aj because this aj is non-zero. Oh, sorry, I wrote it too small, is it? Okay, I will write it again. So what I have written there is Ej is equal to minus of A1 by Aj into V1 plus etc. up to minus of minus of Aj minus 1 by Vj minus 1 plus by Aj into Vj minus 1 plus Aj plus 1 by Aj into Vj plus 1 plus etc. up to An by Aj into Vj. Okay. So in some sense, if something is linearly dependent, there exists one vector which can be written in terms of other. So this vector depends on the other vectors. That is why it's called linearly dependent. Okay. So linearly dependent and linearly independent. So this is another concept. Sorry, I have to rub because this is a small board. So yeah, otherwise I know that things should remain for some time. So I will keep the bottom line for some more time at least. Okay. So now what we will, so we have seen what this linear dependence is and what linear independence is and spanning is and all that. Okay. So now let us define what are finite dimensional vector spaces. See, I somewhere mentioned that something about finite dimensionality and all that. So we say that a vector space is finite dimensional if it has a finite spanning set. Okay, a spanning set is a set which spans. Like the span of that set is equal to the whole vector space. A spanning set is a set is called spanning set if you take the span of those vectors, that gives you the whole vector space. That's called a spanning set. Okay, if a vector space is a finite spanning set, we call that vector space finite dimensional. At this moment, we are not talking about what the dimension of that space is. It's just finite dimensional. Okay. On the other hand, if there is no, like if there does not exist a finite spanning set, we call that infinite dimensional. Again, go back to our example. We will know that Rn is a finite dimensional thing. Why? Because the simple set R2, let's just take R2. 1, 0 and 0, 1 spans. Right? So you can multiply this with x and this with y. So x into this plus y into this gives xy. Using the exact same thing, we can show that Rn is finite dimensional. Using the exact same thing, you can show that polynomials of degree less than or equal to n is finite dimensional. Okay, matrices is finite dimensional, etc., etc., etc. So these are a lot of examples of finite dimensional vector spaces. Now we want to see one example of infinite dimensional vector spaces. Right? Before that, we need to do some work. So let's do that work. Break it now.
As less number of elements than actually a very spanning set. Okay. So let us see. So So we take a spanning set, say U1, etc. up to Un. Okay, this is a spanning set. And this V1 to Vn is linearly independent. Sorry, actually it doesn't matter. Let's call this spanning set. And this linearly independent. So V1 to Vn is linearly independent and U1 to Um is a spanning set. I want to show that this n is less than m. Okay, I will show that n is less than m. Huh? No, we don't know, like this spans the entire V. This we don't know what it spans. We are not looking at what it spans. It's linearly independent. That's all we know about it. This is a spanning set means it spans, so we are looking at a vector space V. So U1 to Um spans V. So every vector can be can be visualized as some say Ci Ui or something like that. Summation Ci Ui. So this is a spanning set and this is linearly independent. I will show that this set has less number of elements than this set. How do we do that? What I do is I look at this set V1, U1, U2, etc. up to Um. Okay? Now this is clearly a spanning set because this itself is a spanning set. So this is also a spanning set. So because of that, this has to be linearly independent. Because this V1 can be written as a sum, since U1 to Um is a spanning set, V1 can be written as a sum of these Ui's. So this set is linearly so this set is linearly dependent. Correct? This V1, U1, etc. up to Um is a linearly dependent set. Correct? So now what we do is we can, so the first thing we should observe is we can what do I say, just a minute. Yeah. So V1, U1, etc. up to Um is, this implies that this is linearly dependent. Okay. So now what I claim is actually in fact what we can show is that okay, so in fact what we can actually do is we okay, yeah, in fact we can be even more specific. This is linearly dependent means that there exists some summation a v1 plus summation ai ui, okay, which is equal to 0, but not all these ai's and a are 0. That is the definition of linearly dependent. But we can be more specific. We can say that this A is not equal to 0. Why can we say that? Because actually what we know is not just that this is linearly dependent. We know something more specific. We know that this can be written in terms of this. Right? So some summation Ci ui is equal to Vi. Correct? So in fact we can take this A to be non-zero. Correct? So we can assume without loss of generality that this A is equal to this this whole set is linearly independent, and such that this Vi is this A is not equal to 0. Apart from A, there should be some Aj which is also non-zero. Suppose every Ai was 0. Okay, if every Ai is 0 here, so I going from 1 to m. If Ai equal to 0 for all m, this implies that A v1 is equal to 0. But A was non-zero, right? So this will imply that v1 equal to 0.